In this video, we're going to look at, I suppose, loop-to-loop type situations. You've got an object inside a cylinder. Now, this could also be a sphere, but when we're taking just a singular two-dimensional plane in the vertical, it's effectively a circle. So you could see it as being a cylinder. You could see it as being in the middle of a sphere. And we've got an object here, and it's just oscillating back and forth, left and right, and gravity is pulling it down. We have a force that's acting from the cylinder surface onto the object. That's the reaction that's creating effectively the centripetal force. If I just show you that as well. So obviously the gravity has a component force acting, the normal reaction, and the sum of those two in the direction towards the center creates the centripetal force. You've got kinetic energy when it's moving, when it's stationary. At the two extremes, that kinetic energy has been used up and it's been transferred into potential energy. You'll notice that all the kinetic energy is sort of spent when it's got to that point, that critical point at the edge there. And if we were to try and change this is an oscillating situation. I'll put in the speed as well. I could show the components of the gravity to remind you you've got two components of gravity. We're only really interested in the one that is in direction towards the center. We're not interested in the one that's parallel, that's that's perpendicular, that's tangential to the direction towards the center. So we're not interested in this green arrow that's pointing effectively in the same direction as the velocity. We're not interested. We're only interested in the what's called FG radial. If I were to increase the speed, we might get a situation where it will go beyond the horizontal. And we can remember from when we had the object attached to a string, the same thing is going to happen there. There's not enough force to ensure that it stays against the side of the cylinder. Let's set that up again. Doesn't quite have enough velocity, doesn't have quite enough kinetic energy. So all this kinetic energy is being spent. Okay, it gets to the point where it runs out, and the whole system collapses and it can't cope anymore. Now, the key thing is the forces that are acting on the object aren't coping. The reaction, that sort of tension that you had with the string, and in this instance it's just a force that's being exerted by the cylinder on the object, goes to zero basically. So you'll see in a second the red arrow is going to go to zero as soon as that red arrow goes. I might try and do that again. I'll try and pause it. So at that critical point there's no force acting from the cylinder onto the object, and it just leaves the surface and flies down as a projectile. So we're going to look at a few questions like that. Now, obviously, before I do that, if I speed it up fast enough, we can actually have the loop-to-loop situations. Let's get rid of the blue arrow for a moment. Actually, no, I'll tell you what, I want the blue arrow. So you can see there, you've got this centripetal force causing it to keep in that cycle. Plenty of centripetal force. Even with the gravity acting, now you can see there's plenty of reaction. That red arrow is plenty of reaction, still plenty there. If it goes too slow, then that red arrow, that reaction force, goes to zero. Once it goes to zero, you've lost your actual sort of circular motion. Right, let's stop yabbering and go on with a few questions. Smooth, hollow cylinder. internal radius 1 meter, make things easier I suppose, it's fixed with its axis horizontal. So just imagine a cylinder, a tube that's horizontal, and there's an object that's going to be moving in a vertical circular motion. Particle of mass m is projected from the lowest point on the inside of the cylinder with speed u. And we're going to look at a scenario where is it oscillating, is it going to do the full loop-to-loop, or is it going to not quite manage that? It's going to go above the horizontal point, but it never gets the full sort of cycle around the top and back down again. So let's look at the different scenarios and let's see how we can do that. Again, primarily we're just going to use the analysis of energy, kinetic energy and potential energy, and we'll see what's going on. So we're using this basic concept of energy at bottom is equal to energy at the upper point. Kinetic energy plus potential energy is worked out for both moments in time, and so half mu squared, so the velocity at the bottom, the height at the bottom is 0, so that's the potential energy. Mgh is going to be mg multiplied by 0, so we have a situation where this is just basically 0, we can ignore it, it's just going to basically be a half mu squared is equal to a half mv squared, so the velocity at the point where it's at its uppermost point, plus mgh. Now, so for these processes, we can assume that the v is going to be equal to 0 in order to find out what's going on. So the key point here, we realize the scenario is v is equal to 0, and see what happens with each of these. So for when u is equal to 2.5, we end up with a half m 2.5 squared plus the 0, not even going to bother writing that in, plus, now we can assume that this is going to be 0. I'll write it in the first time, and we're just interested in seeing what the height is. That's what we're really interested in. What is the height that it gets to? We have a radius of 1 meter, so we can imagine this circle from the center. It's 1 meter down, 1 meter up. The diameter is 2 meters. So from that bottom point, how far up in terms of vertical height and altitude does it get? So if it's less than 1 meter, it's going to be oscillating. If it's more than 1 meter, it's going to get into these regions, the sides here, and then fail. If it is 2 meters or more, we can talk about that in a second, then it's going to do the loop-to-loop. Okay, so let's see what we get here. The m's are going to cancel. We could double everything if we wanted to as well, just to make life a bit easier, I suppose, maybe. But do you know what? A half times by 6.25 gives me 3.125. I'm going to divide everything by m, and we end up with 3.125 equals to gh. And if I divide by g, sorry, so 3.125 divided by 9.8 gives me 0.32. So its vertical height that it has traveled is less than 1 meter, so it's only barely gone a certain height, almost a third of a meter. So it's only just oscillating backs and forwards in such a manner. So it's less than halfway up. That value is less than the radius. Therefore, it's just going to oscillate. So I suppose we could say that if h is less than the radius, we can assume it's going to oscillate. Okay, on to the next one. We have u being 5. And setting myself up in exactly the same way, we end up with, my pen's going all strange this morning, we end up with h being equal to 12.5 divided by 9.8, and that gives us an answer of approximately 1.3 meters. So in this situation, our h is it's greater than r, but it's less than 2r. So therefore, we're going to have this situation where it's going to lose contact. It's going to just sort of turn into a projectile. Okay, it's not going to complete the full turn. It's going to crash. And so the last scenario of 7.5. My pen is gone absolute doolally. So again, if we're looking at how high it gets with 7.5, using exactly the same sort of process. So a half of 7.5 squared, that ends up being 28.125 is equal to GH. I divide by M, and the height ends up being 2.9. Now, you're immediately saying, well, you can't have more than two measures of two radii, as in you can't have something more than the diameter. Okay, it's constricted to inside the circle. So we can effectively say here that because this value of h is greater than 2 lots of the radius, then we can say it loops. Okay, it does the full circle. Now, I appreciate that some people might feel as though, well, this is not possible, but the premise is, and as I said to you right at the beginning, as long as it doesn't lose sufficient kinetic energy, as long as we can keep that tension going, that reaction on the from the circle. So let's just talk about that briefly. So what we could say instead is we could sort of hypothesize. We could say to ourselves, well, do you know what? I think it's going to do the loop. Let's see what the velocity is as it's going through that sort of top arch, and then see what the reaction is. So, slightly different approach here. Wouldn't necessarily work with the first two scenarios, but if we think it's doing the full turn, so we can say to ourselves, okay, let's set ourselves up in the same way. Potential energy at the bottom is 0. Not even going to write that in. Now, let's just say what's going to happen if it had a height of 2. I.e., what's going on? Is it possible, does it work that at that top point, 2 lots of the radius above the starting point, what's its velocity? So rather than us putting v equals 0, let's find out what the v is when the height is 2. So we end up with, now make things easier, I'm going to multiply by 2 here, and I'm going to divide by m. So I end up with 56.25. I end up with v squared, and I end up with 4g. So I've doubled everything and divided by m. So v squared is going to be 56.25 minus 4g. That works out at 17.05, and therefore the velocity is going to be the square root of that, which works out as 4.13. Okay, that's the velocity. So let's just talk, and at the end of the previous video I was talking a little bit about the forces. So we can just imagine what's happening at this top point. Okay, we've got mg acting. We've also got the reaction acting, and those two together add up to make the centripetal force. So if we imagine R plus mg is equal to the centripetal force, if I substitute in what we know, we are going to end up with, and let's just, I'll tell you what, we'll just Hold my horses a second. Let's put in the v squared and the radius, which is 1. So just tidying that up, we can get a reaction of 17.05 lots of m minus mg. Now, it doesn't matter what the mass is. In fairness, now we know what G is. G is 9.8. We end up with 7.25 lots of m. Now, as I said here, as long as you have a reaction, as long as the reaction is not equal to 0, then at that top moment, if you're showing that even at the top moment there is a reaction acting from the circle, from the surface of the cylinder onto the object to help with that centripetal force, then you've got circular motion. So just by working out that that's not equal to 0, we know that it's doing the full turn. Okay, because it's not equal to 0. Or it's greater than 0. I should point out, actually, sorry, because it's a positive value. Okay, because it's greater than 0, then we've got circular motion. You've got the full turn, the full circle. Okay, the loop de loop. Okay, if you could prove that the reaction was less than 0, then the system is failing, and you have one of the other two scenarios. Moving on to another question, very sexist question. A stuntman, boys will be boys, a stuntman wishes to complete a loop-de-loop of radius 5 meters in a freewheeling go-kart. Find the minimum speed the go-kart must be at the bottom of the loop in order to complete the loop-de-loop without leaving the surface of the loop. Assume the loop is smooth. So, yet again, we're just looking at potential energy and kinetic energy. So we set ourselves up there, and we can appreciate, because the radius is 5, we can say that if it's going to do the loop, then that height is going to be 10, 2 lots of the radius. So if we work through that and see what we can tidy up. So that gets us an expression, but we have 2 unknowns. We need to find more information. So we have to park that for a second. We'll come back to it. What we want is, if we're able to get the velocity at the top, then we can work out, therefore, then secondly, what we actually want, which is the velocity at the bottom, the initial velocity. So let's see if we can find out what v is. So this is where the looking at the forces comes into play. So as I said to you beforehand, we need the reaction from the surface onto the object to be 0 or greater than 0. Well, once it becomes 0, then we have a problem, but let's assume that we're just at that point where it's just about 0, just at the top. And the key idea here is that the motion in the vertical circle, okay, it's going to cease when one of the forces is equal to 0, and in this instance, once r becomes 0 here, we have a problem. If it happens right at the top, we don't have a problem. So let's just take the mg plus the radius. This pen is causing me major problems here. And this is going to equal to the centripetal force, so mv squared over r. Now r is equal to 5. So let's assume that r is 0. At this point at the top, if we divide both sides by m, we end up with v squared is equal to 5g. And now we can use that in our earlier equation. So therefore u squared is going to equal to v squared plus 20g. Well, that v squared was 5g, so if we add on 5g plus 20g, we get 25g. Therefore, u is going to be the square root of that, and we end up with 5 root g. If we work that out in a calculator, we end up with 15.65 meters per second. So the key thing is, we're saying to ourselves, we need to have a reaction just at the top, or just about, or literally at that point. We may run out of a reaction, but only just, and the circular motion continues. So there has to be a reaction. If one of those forces is equal to 0, then the circular motion sort of ends. And we'll use that idea again in the next set of questions. Question 4 from exercise 7D would be a question similar to these sorts, so you can have a look at that.